Okay, let's go ahead and start this thing. So as I said in class yesterday, we're going to be looking at transient circuits today. And as much as Caitlin may want to live in a world where calculus is done by other people and not us, this is what we're doing today. So we're going to look at this circuit, which is the simplest possible transient circuit you can have, and then we'll work our way up a little bit from there, maybe. So starting with the capacitor. The capacitor is defined as something that will store energy due to a charge separation or store energy in the form of electric field, and the value is just the ratio of the charge separation to the voltage difference. Right? So the capacitance has a simple definition there. So if we take that and we solve it for charge, we get Q is equal to CV, or QVC. Why did I do that? Because now I'm going to take the derivative of both sides. The derivative of Q is a variable, right? Because we can have more or less charge in the capacitor. Derivative of Q, of course, would be dQ dt, because I'm going to take the derivative with respect to time. I did not specify the time. Take derivative with respect to time. dQ dt, though, by definition, is current. So by taking the derivative of this equation, we see that the current going through a capacitor relates to the rate at which the voltage changes, which makes perfect sense. You might have noticed that half of the class period yesterday was me waving my hands on that topic. You know, that when you start out, you have no voltage on there. You have a lot of current, but for each charge that comes across, the voltage rises, and so it slows down. So this is going to be our key equation. Now let's think about some ramifications of this before we move on. So how many people have seen that equation before in another class? 3? How many people have taken the circuits class? 3? Okay, just making sure it's the same group. So ramifications of this, and you 3 don't have to answer because you should know the answer already. Does this equation set any restrictions on, well, the answer is yes, okay? The answer is yes. Does this equation set any restrictions on voltage or current for a capacitor? The answer is yes. Now the real question is, which one or both? Okay, I had to answer current. Why does it set a restriction on current in your opinion?
It's directly based on time.
Okay.
So there's a certain amount of charge that'll move in a single amount of time.
Now, in my opinion, it doesn't, but I'm going to work with you, Gabriel. Okay. What this does, because current is the rate at which charge is flowing, you can't have an infinite charge move in no time. Agreed? So there is a limit, a practical limit on current, that the current has to be less than infinity. It could be very high. You can have a lot of charge flowing in a very short amount of time. But you can't have an infinite amount of charge flowing in no time. Right? Either one of those would make an infinite current. So you can't have an infinite current. It has to be finite. But if you have a finite current, what does that say about the voltage in this equation?
It's also finite.
It doesn't say the voltage is finite, although it turns out it's going to be. But it says something else. Okay, go ahead, you 3. What does it say about the voltage, or the voltage? The voltage cannot change instantly. Why? Because if the voltage changes instantly, what's the derivative of the voltage with respect to time? Infinite. And so, oh, come on. Did I? No, this is the right one. I just can't scroll on this one for some reason. That's weird. Hopefully I will be able to scroll on the next one because I plan on using it. So this sets a condition of finite current implies, it actually demands, implies, not spelled that way, that voltage is continuous. Continuous means that it does not jump. It can't go from 1 volt to 2 volts. It has to continuously move between 1 and 2 volts. Good, this one scrolls. It's just that one that's broken. So we're going to use that to solve this simple circuit. Now the circuit has a switch that can go in 2 positions, so I'm going to solve it both ways. I'm going to start with the harder position, of course, with the switch in position A. It's going to be charging that capacitor. So the key here is the switch has been in position B for a very long time. If it's been in position B for a very long time, we have the capacitor connected to a resistor. Any voltage difference on the capacitor then is going to cause charge to flow through the resistor. And what does the resistor do to energy? It dissipates it. So the energy that was stored in the capacitor will have been dissipated by that resistor until after an infinite amount of time, the capacitor has no charge on it, no voltage. So that's our starting condition. Capacitor starts with no voltage on it. Then I flip the switch to position A, and I want to know what's going to happen to the circuit. Right? That's the idea of a transient circuit. So I flip the switch position, and I'm going to apply Kirchhoff's voltage law to my circuit. So I only have one loop when I have the switch in position A. And so with that one loop, what's my Kirchhoff voltage law equation? Somebody who's brave, just start spitting it out. Well, first of all, what is Kirchhoff's voltage law? Okay. Make sure we have that specified before we start. So somebody just, start here, let's say, and what do you have as you go around this loop for your equation? Okay, positive VB. Minus IR. I'm using a lowercase I. I actually wrote that down here. Using lowercase letters for current, charge, and voltage, because technically the lowercase means that they can change. The uppercase means they're not changing. So I'm following the technicality here, which oftentimes you'll see is not followed. Okay, so minus IR, and then one more thing before I get too hosed here. What direction should the current be flowing in this circuit? Okay, so the current should be flowing like this when I first flip the switch, because it's going to charge that up. And so I'm going to get a positive charge on the top and a negative on the bottom. And so for our sign conventions, we define the sign convention the same way as we do for a resistor. Right? The side that the current's going in is the side we're going to consider positive. The side it's leaving is the negative. And so the voltage across the capacitor is going, if I go from this side to this side, I'm going down, right? So I'm going to put minus, and I'm just going to put V sub C for the voltage of the capacitor. I might have said Q over C, but I didn't want to. Everybody okay with that? You just get a different integral equation. It still works if you do that, but I wanted to do it this way. It made me happier. So what's that equal to? 0. And when you look at that, you see an equation that has current and voltage, 2 variables. And what does it not have? We're doing a transient circuit, a circuit that's changing in time. There's no time there. So this is a true equation, but I'm going to need to do some adjustments to make it so I can find time relationships from it. And what's the obvious adjustment? We had from the preceding page that the current through the capacitor is equal to C dV capacitor dt. So I'm going to substitute that in for the current. So it's going to give me VB minus C dVC dt r minus vc equals 0. Now I'm going to solve this for the derivative before I move further. You don't have to solve it for the derivative, because what we're going to try to do is, solve for v as a function of time. But to me, it makes the process easier if I first solve for the derivative. So to solve for the derivative, I am going to move this to the other side by adding I forgot there's an R there. You can already see, hey, I think I might see where RC comes from, right? Because I have an RC in there. I'm going to leave it there. I'm not going to substitute now and say, oh, this is going to be useful to me, but we can see that it's there. Now, if I want to solve this, what kind of equation do I have? I have a linear first order differential equation. And these are ones that are within your ability to solve. So do you remember like the first Tuesday of first semester when we did this? A little bit. What do we have to do to solve something like this? That's right. We have to separate the variables. What are the variables in this equation? VC and, I heard somebody say T. So we look at this. What do I have to do to separate the variables? Okay, multiply both sides by dt is the first step, but not the only step. What's the other step? I have to divide VB minus VC from both sides as well. Now I'm going to divide RC by both sides as well. So I'm going to do 3 steps in one. Divide by RC, divide by VB minus VC, and multiply by dt. And what that's going to give me is dVC over VB minus VC is equal to dt over RC. Correct? Yeah. No sign errors. That's what I was looking for, was to make sure I didn't make a sign error. All right. Who can integrate the right side of this equation? Yeah. Everybody, once they look up, says, yeah, I could do that. You can integrate the two sides independently. Why can you integrate them independently? Because they're equal to each other, and each side only has one variable. And so you just integrate both sides from initial to final. Whoa, that's a funny F. And as long as you're integrating from the same start to the same end, it's going to still have to be equal. So the right-hand side was simple. What do we get when we do the right-hand side? Okay, putting in our limits, that would be T final minus T initial over RC. Usually, we go ahead and say T initial is 0. We can set our initial time wherever we want. But there will be some cases, not in my class, but in the circuits class, where you do things like, I start with the switch in position B, I flip it to A, and after 2 seconds, I flip it back to B. And in that case, you might want to leave the T initial in there. But for our purposes, I'm going to go ahead and apply that T initial is equal to 0. And so that's just equal to T final over RC. The left side, what do we have to do on the left side to integrate this? What? Not separate. It's already separated. VC is the only variable there. you say, Aaron?
Can you do U substitution?
That's what you do. You do a U substitution. So we will simply define, let U equal VB minus VC. So that means du is equal to minus dVC. And this becomes, I ran out of space, the integral from initial to final conditions of, notice there's a minus sign there because it was minus VC. So it's going to be minus du over u. But if you do the integral of du over u, what do you get? Natural log. Don't forget the minus sign, so we have minus natural log of u, and being real clear, putting in the limits, u final over u initial. So what I found by doing this problem is, next page, minus natural log of u initial, u final over u initial is equal to T over RC. Of course, I have to put u back in. U is equal to VB minus VC. Let's move the minus sign across in the same motion. Are you comfortable moving the minus sign across? Thank you. So I'm going to have natural log of VB minus V, and I'm dropping the F. The final is whenever I want to know. Divided by VB minus V initial equals minus T over RC. Now there's really only two steps. You have to get rid of the natural log and then you just solve for V. So how do I get rid of that natural log? Exponential, because it's the inverse function. So I'm going to have VB minus V over VB minus V initial equals e to the minus T over RC. Multiply across by the VB minus V initial, and I'll have and finally, solving this for V, the voltage across the capacitor at any time is equal to VB plus, and I'm moving the VB minus VI term across the equal sign, so it's going to be a negative. Instead of writing a negative, I'm just going to reverse which one's negative inside. So I'm going to put the V initial first, and then the VB final. And that's the equation that tells me how the voltage is going to change with time across my capacitor. So what was the V initial for my capacitor? It was 0 because I'd had it in the discharge position for a very long time. But you can see that this equation would work if I had had it charging for a while, discharging for a little, and then back to charging. I would just start with a different V initial. And the VB is the voltage it will have after it's fully charged. And so I usually take this and I write it in a generic form. The generic form works always, and it doesn't matter if you're looking at a capacitor like we did this or an inductor. So the voltage across my element, I'll put C here, is equal to the voltage at time equals 0 minus the voltage at time equals infinity, e to the minus T over R, well, let me put tau so that it always works, plus the voltage at time infinity. Because the VB was the voltage it reaches after an infinite amount of time in that position, and the V initial was the voltage it had right when you flip the switch. Now remember, right when you flip the switch, before you flip it and after you flip it, it has to be the same voltage because it can't jump. It has to be continuous. So that V0 would be the voltage just before you flip the switch, because that's also the voltage just after you flip it. So this equation works for any capacitor. All you have to do is find what was the voltage of the capacitor immediately before you flip the switch, and what will the voltage be if you leave the switch in the new position for an infinite amount of time. And finally, what are the resistance and capacitance seen by that, or what is the resistance seen by that capacitor? I said incapacitance. What is the resistance seen by that capacitor? So if I had something crazy like this, and here's my switch. So I'm just going to switch it from the open position here to the closed position. What would my voltage 0 be? Okay, I heard somebody say 0. Why 0? Okay, when that switch is open, there's not going to be any current flowing anywhere. But I have a resistor in parallel with that capacitor, so the capacitor will discharge through that resistor in parallel with it. What about my voltage after an infinite amount of time? It's not the voltage from the battery. After an infinite amount of time, how much current has to be flowing through the capacitor? When it's reached equilibrium, how much current is flowing? 0. So I can take this and analyze, okay, after an infinite amount of time, the current for the capacitor is going to be 0. So if I look at that circuit, I can ignore the capacitor for the infinite time and just say, I have these two resistors with current flowing through. And so I could just solve it. I have a power supply, R1 and R2. And so now those three of you who've taken circuits, you know instantly, oh, well, that's a voltage divider. What's a voltage divider? It's when you have resistors in series and you just look at the voltage across one of them. In that case, you have the current at infinite time is equal to the EMF divided by the total resistance R1 plus R2. And so the voltage across R2 is going to be resistance 2 multiplied by the current, which turns out to be simply the EMF multiplied by R2 over R1 plus R2. So that's our infinite time voltage. Notice this is going further than we did in the general physics class because we're looking at a situation that's not totally simple like we started today. What about the resistance in the RC time constant? I said that it's the resistance seen by the capacitor. Well, if you look at this capacitor, the capacitor sees that there's R2, then it sees R1 and a voltage supply. 3 people here know what to do with that voltage supply. Everyone else is like, hey, voltage supply, I don't know. Well, here's what you do. If it's the voltage supply, what is its resistance? The other one. 0. If it's a voltage supply, it has an effective resistance of 0. If it's a current supply, it has an effective resistance of infinity. It's easy to get those confused. Now I'm questioning myself, but I'm pretty certain. And so we look at this and we say, okay, if that voltage supply has a resistance of 0, the capacitor just sees 2 resistors in parallel. And so the resistance seen by the capacitor is R is equal to R1, R2 over R1 plus R2. Gabriel, you have a question.
You mentioned the difference between a voltage supply and a
Current supply.
current supply. What is the difference between those?
Well, a current supply, no matter what circuit you have it connected to, it supplies a constant current.
Okay.
A voltage supply, no matter what circuit you have it connected to, it supplies a constant voltage.
Okay.
And so an ideal battery is a voltage supply. And that's all we've dealt with in this class, right? Well, we've dealt with batteries with an internal resistance so that we can give ourselves a Thevenin equivalent circuit for, we're not going to learn about Thevenin equivalent or Norton equivalents. Three of you can probably relax just a little because that's where you use this a lot, right? What's the equivalent resistance for them? Okay, so there's our resistance. So then what's the time constant? Yeah. It wasn't a complicated question, just making sure we understand why I had to find that equivalent resistance. And so now I have all of the values, this value, this value, and this value, to put into that equation so I could say the voltage at any time is equal to the initial voltage, which is 0, minus the infinite voltage, which is e to the minus t over c R1, R2 over R1 plus R2. That looks beautiful. And then plus you obviously would probably want to simplify that, wouldn't you? Most people would say, hey, that is times 1 minus e to the minus t over, and I'm going to go back to writing tau because that was too long to keep writing the full thing. So that gives us the equation for the voltage as a function of time. Now I have the voltage as a function of time. What if I want to find the current? Yeah, we started this derivation with I is equal to c dv dt. So to find the current, I just need to take the derivative of this. So the current is that, which actually turns out to simplify and you see those cancel, that cancels, that cancels. So now we've done the full and complete derivation for how you get the transient behavior for a capacitor. And we can see how you go from getting that voltage equation to getting the current equation. I was initially going to come back and do this again, but put the switch in position B. If you put the switch in position B, what's different for applying Kirchhoff's voltage law? There's only one difference.
You take out the battery.
Yeah, you take out the battery. That's the only difference. And so you just take away this VB from your differential equation. You do all the same work. Right? You don't need to use substitution at that point. It's just a little simpler. So there's really no point in repeating it. If you can do it the one way, you can do it the other. So Conclusion from this. We found this equation here, and we said by taking the derivative, I can find the equation for the current as well. There I have a current equation to compare. Now that current equation looks exactly like the voltage equation, except for all V's have been changed to I's. If you have a capacitor, what is the I infinity always going to be? 0. Because when you reach equilibrium, your capacitor is no longer changing its voltage, hence the current has to be 0. So you're always going to have, for a transient circuit with a capacitor in it, the I infinity is going to be 0. So that just becomes I initial e to the minus t over tau. So the capacitor current curve is always going to look exactly like the purple line here. Where it starts and the time factor, the height that it starts at and the time factor for its decay depend on the circuit. But it always has that shape. The charging one, if you start at 0 volts, will always have that shape. But you could start somewhere else and it would just be shift over to that starting point. And that's what the difference of the initial not being 0 is going to be, is shifting over on the starting point. So that's my transient circuit analysis. I suppose I could start in with the inductor transient circuit, but you know what? Only 3 people would that mean anything to. The rest would be, I don't know what he's talking about. He's doing math about something I don't understand. That's really not very beneficial, is it? No, Caitlin, you did understand this. So, any questions?
You keep saying transient circuit. I'm a little unclear of the definition.
Okay, so transient means you're changing between one state and another state. So we have DC steady states, is all that we stayed up to yesterday. And then transient is changing between one DC steady state to another DC steady state, but it's not steady in between. And so that's what the transient is.
So is it only transient while it's changing?
Yes.
Okay.
Here.
Is that the same as degenerate? Or I thought I saw a concept coach using that term or something. Maybe that was getting into magnetism or something. I'm not sure.
Without seeing the context, I can't be certain, but I know when I think of degenerate, I think about, states that are degenerate, like there's more than one way to get this state. And that can't be what we're talking about here, I don't think. So I'm not sure on that with the context. Okay, any questions about the homework that's due today? Because I think it's supposed to have been due at the beginning of class, but I didn't collect it. Any questions about it?
You can submit it online, right?
Yeah. Everybody feels good about it? Everybody's giving up on the things they don't feel good about. I'm more than happy to field questions. If you don't have any questions, though, I guess we can end class.
Aaron is a really good teacher. I just want to say that.
Thank you, Aaron.
I sat in Dr. Webb's office for like 7 hours last week.
Not 7 hours. It was like an hour and a half. And I told her to go teach you guys, so she did what I told her to do. Did she teach you too, Jonathan?
Yeah.
All right. Good. Don't want you to be left out since you're not on campus.
No, yeah, I came here and we all worked on it.
Yeah, I wish I'd be able to come Sunday too. Okay, that was slightly less productive.
That's fun.
Okay, well, I guess we'll end class. And once again, thank you, Aaron. I really do appreciate you spending your time to help them.
Well, hopefully not everybody else got the same things wrong that I did.
What if you got them all right, like I suspect?